right, let's talk about redox. Let's remind ourselves about redox reactions. So this video is really meant to be a review for people who have seen redox reactions before, but maybe haven't thought about them in a while. So redox stands for oxidation and reduction reactions, hence the redox part. So the red ox gives you your oxidation reduction reactions, and it's really about the movement of electrons. So oxidation is any chemical process where electrons are lost. Reduction is any chemical process where electrons are gained. And of course, reduction and gaining is counterintuitive. The language with redox is a little bit frustrating. So there's a couple mnemonics that you can use to memorize these things. I like oil rig. That's what I always learned going through school. Oxidation is loss of electrons. Reduction is gain of electrons. Or if you're a fan of Leo the Lion, Leo goes grr. Loss of electrons is oxidation. Gaining electrons or gain of electrons is reduction. So that's kind of quick ways to remember which one is which, because again, the language is a little bit counterintuitive. So in order to figure out whether or not an oxidation or reduction process is occurring for particular elements, you need to assign what are called oxidation states or oxidation numbers. And there's kind of 5 general rules for those. There's kind of rules for general compounds, but then there are also rules for individual elements. So for the first one, elements in their elemental form are always going to have an oxidative state of 0. And of course, elements in the elemental form is a little bit redundant, but I committed to writing it, and there it is. Okay, so if I have something like gold, then gold's oxidative state in this form, it is the way that gold exists on the periodic table, that would be 0. If I had oxygen, which is diatomic in nature, then even though there's 2 of them paired together, it's still in its elemental form. Sulfur, for example, is S8 in its elemental form, so that would also have an oxidative state of 0. So it doesn't matter how many there are. If you're in your elemental form, that's 0. If it's by itself, then you put the 0. All right, so for monoatomic ions, the oxidative state is the charge on the ion. So if I have a sodium ion, for example, and I would know that I have an ion because I have a metal with a nonmetal, so I have a +1 charge here on my sodium ion. That means I have an oxidative state of +1. Or if I have a phosphorus ion, so phosphide has a 3- charge, so that means that my oxidation state is a -3. Okay, so the charge on the ion is equal to the oxidative state. And of course, just to make it extra confusing, the way that we write the charge is the number and then the sign. When we're talking about an oxidative state, we usually do the sign and then the number. So again, that's for monoatomic ions. For polyatomic ions, the charge refers to the entire group of elements, and you'd have to figure out the individual oxidation states for each of the elements within the larger polyatomic, and we'll talk about that in a second. Now, hydrogen in a compound is always +1, except when it isn't, because sometimes it's -1. But for most compounds that we find hydrogen in, it's going to be +1. The exceptions are really when it's paired with metals. Then it tends to be the -1. There's a couple other exceptions, but +1 in general. Oxygen in a compound is -2. You would think, well, why am I saying that? It's a little bit redundant, but oxygen can be in covalent compounds where it doesn't have a 2- charge, but it still is going to have a -2 oxidative state. And fluorine, because of its electronegativity, is always a -1. So whether or not it's an ion, that would be its charge, but in a covalent compound, it also has an oxidative state of -1. So these are our oxidation rules, how we assign oxidation numbers. Now let's apply it to a problem. So I have my chemical equation here. I have calcium with potassium nitrate. That gives me potassium and calcium nitrate. So if we were to do this reaction and we wanted to say, is this a redox process, then the first thing I need to do is apply those rules and assign the oxidation numbers. So if I look at my calcium here, it's all by itself. It's all alone, so it is 0. Now if I look at my potassium nitrate, I know that potassium is in its ionic form because it's a metal with a group of nonmetals. So that means that my potassium is +1. We know that our rule for oxygen is that oxygen is always a -2. So that's going to be a -2. And we don't have a rule about nitrogen here, but there's a couple ways we can figure out nitrogen based on what it's paired with, because all of the oxidative states in a balanced neutral chemical compound have to equal 0. So that means that my potassium plus my nitrogen plus 3 times my oxygen all have to equal 0. So I have +1 plus whatever my nitrogen is plus 3 times my oxygen, all of that equals 0. And now I can see that I have, +1 minus 6, so nitrogen -5 equals 0, so nitrogen must be +5. Now that's always going to be the case with nitrogen and nitrate. The other way to do this is that I know my nitrate because I know my polyatomic ions and I know my charges on them. Then I could say, well, if I know nitrate, then I know that nitrogen plus 3 times my oxygen has to equal -1. So it equals the net charge on that polyatomic ion. We know that oxygen is always -2 in a compound. And then we'd still end up with our nitrogen is equal to +5. So you can think about it either way, as either kind of the whole balanced compound and setting it equal to 0, or if you're snappy with your polyatomic ions, then that gives you that as well. All right, so here's our oxidative states, our oxidation numbers for our reactants. Now let's go to the product side. If I look at potassium here, it's all by itself. I have a colleague who likes to call this the single ladies rule, because when it's single, then you got to put a ring on it, right? Calcium is a metal, and it's paired with nonmetals, so it is in its ionic form. It's going to be the charge on that ion. We know that calcium is one of our alkaline earth metals, so it always has a charge of +2. And then because this is nitrate, and nitrate stays the same, and it's always going to have the same charge, because oxygen's always going to be -2 in a compound, then that means that this is going to stay the same here. So my oxygen's -2, my nitrogen is a +5. So if we map out what's happening, with oxidation numbers, we're looking for a gain in oxidation state. So if I increase my oxidation number, then that's oxidation. So if I'm increasing my oxidation number, that means that I'm getting more positive, which means that I'm losing electrons, and oxidation is loss. If my oxidation number goes down, that's reduction. And there's where the term actually makes sense, right? So reduction makes sense in this context because our oxidation numbers are going down. So what is being oxidized and what's being reduced? Well, we can kind of write out our half reactions, which show the redox in the above reaction, because not everything changed. So our nitrogen didn't change, our oxygen didn't change. So those aren't really part of the redox process. They're kind of spectators in all of this. They're hanging out, they're part of the chemical compounds, they're part of the chemical process, but they're not actually part of the redox reaction. So let's do our oxidation half reaction, which is just going to show the loss of electrons. So which one is being oxidized? Well, it's the one that's getting a larger oxidation number going from reactants to products. Calcium is going from calcium in a 0 oxidative state. So some people will put the 0 up there as a charge, or actually as the oxidation state. So I'm going from calcium 0 to calcium 2+. And how do I do that? In order to do that, I need to lose 2 electrons. So if we're thinking about balancing out the charges here, I have a positive on this side, so my electrons must have to be on this side. And I need 2 of them to balance out the 2+ charge. Now electrons on this side of a reaction like this indicate loss. So they're a product, so they are being lost in the process. Now reduction is gaining electrons. So if we're thinking about this in the context of our reaction above, which one is reducing the oxidation state? Well, that would be my potassium. It's going from a +1 to a 0. So I have 2 potassiums on this side. They're in +1 oxidative states. And then I'm going to 2 potassiums on this side that have, no charge. So again, you can either think about it as just potassium neutral, or you could put your not up there, your 0, to say that it's in a 0 oxidative state. And in order for these charges to balance out, right, a neutral on one side, I have 2 plus signs on this side, so I need to gain 2 electrons in order to make that true. So I'm indicating that electrons are gained because they're on the reactant side. And if I look at the oxidation and reduction halves of this reaction, the two half reactions, then they have the same number of electrons lost as gained. And so that's an important piece to this. We have to lose the same amount that I'm gaining because they have to go somewhere. It's not like I'm losing these and then I never see them again. They're picked up by that potassium. This is a physical representation of the movement of those electrons in the process. Now, here's the other kicker in terms of language, right? Here's the oxidation side of it. My calcium here is being oxidized. So we say that it's the reducing agent. So an agent is something that allows for something else to happen, right? Like a CIA agent or something is out there making things happen. So the calcium is the one that's allowing for electrons to be gained because it's losing them. And then in my reduction here, my potassium is my oxidizing agent. And so by taking those electrons, we're allowing for that process to occur. All right, so that's kind of a quick little review on oxidation and reduction, or redox chemistry, assigning oxidation numbers, and I'll be talking to you more about electrochemistry in future videos.